The last video for section 4.4 is going to show a way that you can prove that a function is uniformly continuous on a set without needing to use the definition. And so I've written out the definition of uniformly continuous here on the left-hand side. And I've also written out the sequential criterion for the absence of uniform continuity on the right-hand side. This is our way of proving that F is not uniformly continuous on A, and we do that using sequences. The theorem that, the main theorem that I'm going to present in this lecture is about uniform continuity on compact sets. So it says that if F is continuous on a compact set, so we need to know we're compact here, and we also need to know we're continuous, then that's enough to actually say that F is uniformly continuous on A. Now, in general, we know that continuity doesn't imply uniform continuity. Just because you can get a delta for each C doesn't mean you can get a delta that works for all C at the same time. However, when you know your domain is compact, it turns out that continuity and uniform continuity are actually equivalent to one another. And the way that we're going to prove this theorem is by contradiction. What we are going to do is assume that our function is not uniformly continuous, which gives us two sequences from our sequential criterion for the absence of uniform continuity. So I'm going to outline what we're doing here. So assume F not uniformly continuous. Apply sequential criterion for absence of uniform continuity to get two sequences. Now, remember, our assumptions, if we're doing a proof by contradiction, is we still get to assume that F is continuous and that we're working on a compact set A. And notice that if we assume that F is not uniformly continuous, that introduces sequences into the picture. And we have, for continuity and for compactness, we have a sequential criterion for both of those. So for continuity, we're going to use the sequential characterization of continuity. And just recall that says that when F is continuous at some point C, that's the same thing as saying that for any xn that you pick in your domain, if xn converges to C, then f of xn converges to f of C. And then we're also going to use the sequential definition of compactness. And that says that when your set is compact, that is equivalent to knowing that for all sequences that you select from your set A, there has to be a subsequence that converges to X where X is an element in A. So notice that if we get this convergent subsequence here, because our function is continuous at any point in A, we're going to be able to sort of plug in, so in particular we're continuous at X and A, we're going to be able to use this sequential criterion, but we're going to use it on X and K. because x and k is still a sequence in our domain where we know we're continuous. And so basically we're going to get a contradiction. We're going to find that on the one hand, our function values between xn and yn have to be close, but on the other hand, the sequential criterion for the absence of uniform continuity tells us that the difference between the function values on the two sequences is supposed to be greater than or equal to epsilon. So I'm going to take us through the proof, and hopefully it makes sense. So this proof again is by contradiction. So I'm going to assume the hypotheses. So assume f is continuous on A and A is compact, but f is not uniformly continuous on A. So then by theorem, the sequential, the one with the crazy name, by theorem, there has to exist an epsilon greater than 0 and two sequences, xn and yn, contained in A, such that if you look at the inputs along that sequence, those two sequences, they're getting closer together, going to 0, their distance. But the outputs are always going to be greater than or equal to epsilon apart. And this is true. Remember, this is true for all n. So no matter what inputs you select from your sequences, we need to see that the outputs are greater than or equal to epsilon apart from one another. Now, these sequences that I've introduced, xn and yn, I don't know that they converge. I just know that they're close together. They could both diverge to infinity, for example, but stay close together. So what I want to do here is apply the definition of compact so that I can get a convergent subsequence of xn. The reason why I want to do that is because I cannot use my assumption that f is continuous at a point C until I know that I have a convergent sequence that I'm working with. And since I cannot assume xn is convergent, I can't use xn. However, I can use an xnk that has to converge by the definition of compact. So because xn is a subset of A, so this is a sequence in A, and A is compact, there has to exist this subsequence x and k that converges to x, where x is an element of A. Now that I have a convergent input sequence going to a point where I know my function is continuous, I can apply the sequential characterization of continuity. So since f is continuous at x in A, f of x and k has to approach f of x. Whenever you have a sequence approaching a point where the function is continuous, if you evaluate f on that sequence, it should go to the actual function value there. Now, I want to try to say something about, sort of the key here is remember what we're assuming. We're assuming that our outputs here are always far apart. And so what I want to try to do is take a look at some outputs. I want to look at xnk and then also the corresponding subsequence ynk and try to show that I get a contradiction to that distance assumption that I've made for the outputs. So what I want to do now is take a look at the sequence ynk and see what it does. So notice that if you take the sequence y and k, that is the same thing as looking at y and k minus x and k plus x and k. So all I've done is added and subtracted a term from the subsequence x and k. Now the reason why I did that is because we have this other assumption up here that we know that any values in my sequence xn and yn have to be close together and they're converging to 0. So if I do this, I can now apply the ALT because I know that y and k minus x and k as a sequence has to converge to 0. So I'm thinking of these as two sequences. This is going to 0, and then remember x and k was our convergent sequence that went to x. So remember what I'm saying here is xn minus yn going to 0 implies that if you look at x and k minus y and k, that also has to go to 0. And notice, we've changed the order of subtraction here, but that doesn't matter because if x and k minus y and k goes to 0, then any negative multiple of that sequence will go to 0 as well. Okay, now that we have that, and this is by the ALT, I guess I should have written that, so by ALT. So now that I have that, I want to take a look at what happens with f of y and k, because notice I didn't know yn converged, but now I know y and k converges, which means I can apply continuity to that as well. So again, by continuity at x, I have a subsequence y and k converging to x. So I know that f of y and k has to converge to f of x. So if I look at the ALT, now what I've really shown here is that the difference in my function values along these subsequences has to be going to 0 since both of them converge to f of x. So by the ALT, if I look at f of nk minus, f of xnk minus f of ynk, that sequence of values has to approach f of x minus f of x, because we just got done showing that's where the outputs along these subsequences go. They both go to f of x, and that's just 0. That's a contradiction, though. We assumed that f of xn minus f of yn was greater than or equal to epsilon for any n that we took a look at. And in particular, that means that any subscript I pick that's in the subsequence should also have that constraint. So we assumed that that was greater than or equal to epsilon for all nk. But we're supposed to have a capital N in the natural numbers such that for all nk in the tail, so all nk greater than or equal to capital N, we're supposed to get that f of nk, f of xnk minus f of ynk is less than epsilon, because that's the definition of convergence to 0. So we've directly contradicted our distance assumption for our outputs, and so therefore f must be uniformly continuous on A. So now we have this really nice tool that tells us, given any continuous function, if you know that you're working over a compact set, you can automatically apply this theorem to say that your function is actually uniformly continuous on that set. And you can do this without having to reprove the definition of uniform continuity. So for example, if I take a look at the function, just the square root function, I could say that this is uniformly continuous on the compact set 0, 1. The proof of this is literally just referencing the theorem we just proved. So f is continuous on the compact set 0, 1. So by theorem, f is uniformly continuous on 0, 1. Now, something I want to point out about this function f of x equals square root x is that it has something similar, something a little bit funky near 0, that's similar to kind of what happened with 1 over x. And remember, we said 1 over x was not a uniformly continuous function if we had a domain that allowed us to go up near 0. So notice here, if you take a look at the derivative of your function, we know from calculus that that gives us 1 over 2 root x. Now, that's going to go to infinity as x goes to 0, which says that my function is changing very rapidly near 0. And that would seem to give us the intuition that because we have this unbounded derivative, maybe that means we're not uniform continuity or uniformly continuous. But it turns out we are using this theorem. So something I want to point out is that the limit as x goes to 0 of my function of square root x exists. And that's a distinction between what happened with if I used the function 1 over x and I look at f prime of x, that's negative 1 over x squared, just using derivative rules. And that goes to infinity as x goes to 0. But the distinction with that function is that the limit as x goes to 0 of the original function, 1 over x, equals infinity. In other words, does not exist. So this is pointing out to us that just because the derivative is unbounded doesn't mean that you can't be uniformly continuous. In the event that the place where things get a little bit funky, so where the derivative is unbounded, in the event that that is a place where the limit of the original function exists, it turns out there's a way to recover uniform continuity. So I'm going to show you an example that is going to demonstrate how we can do that. So here's my example. So f of x is going to be the function x sine 1 over x. I want to prove that f is uniformly continuous on the open set 0, 1. So if I take a look at a picture of what this function looks like, I mean, we've seen sine 1 over x before. It oscillates wildly near 0, but the fact that we're multiplying by x is actually going to slowly kill off that amplitude. So we're going to have this function that has large amplitudes away from 0, but then it's going to, even though it oscillates like crazy, it's going to go down like that. Now there's a hole at 0 because we cannot plug in 0. And then on the other side, it gradually builds back up to large oscillations. So this is y equals x sine 1 over x. If you take a look at the derivative of this function near 0, it is unbounded because the fact that you're oscillating so quickly leads to rapid rate of change. But something I want to point out here that's important is that the limit as x goes to 0 of x sine 1 over x actually exists. It's equal to 0. You can prove that using the squeeze theorem. Now, notice that the set that we're working on is not a compact set. So I can't just say, oh, I'm continuous on 0, 1, and so therefore I have to be uniformly continuous on 0, 1. We cannot, as is, use the theorem that we've just proven. What I would like to do is extend my function to be continuous on a compact interval and then apply the theorem. So here's how this argument is going to go. So our goal is going to be to extend f to be continuous on the compact interval 0, 1. Then we're going to use the fact that if f is uniformly continuous on some set A, then f must be uniformly continuous on any B such that B is a subset of A. So we're going to look at this continuous extension. We're going to say, now that we're continuous on a compact set, that extension must be uniformly continuous on the compact set. And then we're going to restrict the function back down to just the interval, the open interval 0, 1, and we'll notice that that's just the same function that we just said was uniformly continuous. So the one thing we need to point out here is, why can we extend f to be continuous at 0? Because remember, we said in our graph there was this hole. The reason why we can do this is because the limit of our function exists. So the actual graph of the function we're given, x sine 1 over x, has a hole in it at 0. What we're going to do is we're going to define our function to fill that hole in. That new function that fills in the value at 0 to be the limit value at 0 is going to be our continuous extension. So again, we can do this because the limit as x goes to 0 of f of x exists. This is an example of what you probably learned or saw called a removable discontinuity when you took calculus. And so I can use this L value as f of 0. So I'm going to let g of x be the function that's equal to f, so x sine 1 over x when x is not 0, and equal to 0 when x is 0, because that's the value of the limit. So again, this is the limit as x goes to 0 of x sine 1 over x. Now, I know that this function g is continuous at 0 since, well, I could just use the limit characterization of continuity. I could take the limit as x goes to 0 of g of x. That is really the limit as x goes to 0 of x sine 1 over x. The reason why I use that branch of g is because when the limit is approaching 0, you're not right at 0. So I want to be using the branch for when x is not 0. But by definition, we said, okay, well, one, we know that limit exists and it's 0, and by definition, that is the value of the function at 0. So we have proven that g is continuous just using the limit characterization of continuity. Another way you might say this is that g is continuous, I guess you also need to say that g is continuous away from 0. It's continuous when x is not 0 because it is the product of continuous functions, x and sine 1 over x. When x is not 0. And this is the ACT here, the algebraic continuity theorem. So therefore, what we found is that g is continuous on this compact interval 0, 1. And since 0, 1 is compact, by theorem, the theorem we just did, g is uniformly continuous. On 0, 1. And so in particular, g is uniformly continuous on the open interval 0, 1, since 0, 1 is just a subset of the closed interval 0, 1. But notice g equals f on 0, 1. Because remember, this function g, as long as we're not at 0, is really just the function f. And so what we've really shown is that f is uniformly continuous. On 0, 1. So basically what we've done here is we've picked a compact set containing 0, 1. If f is not continuous on this larger set, but the limit of f exists where it fails to be continuous, then you can extend to a function g that fills in that hole and then apply the theorem. So I'm going to write that out real quick. Pick a compact set containing 0, 1. If f is not continuous on the compact set, but the limit of f exists at the place where continuity fails, extend to a function g that fills in the hole. Then apply the theorem.